And it doesn't matter to me necessarily where we begin, but let's talk about the relationships between pressure, volume, temperature, and your number of moles. Seems as good a place to start as any. So P is going to be our pressure. V is our volume. N is the one that people tend to forget. So remember, that's going to be your number of moles. And the nice thing about moles, and the reason we use it, is that when we're comparing our compounds, when you have a number of moles, it's always going to be based on that 6.02 times 10 to the 23rd. So if I have 1 mole of oxygen, that's going to be the same number of atoms as if I have 1 mole of hydrogen. So when we're comparing moles, the numbers are always the same no matter what the element is. Obviously, my masses will be different, but for our purposes here, we tend to compare things by moles because then it doesn't matter what the substance is. The number of moles would stay the same. That makes sense? All right. And so then we've got volume and we've got temperature. And one thing you do want to remember is temperature we're mainly going to have in Kelvin. And then volume is mostly liters, but we'll get more to that later. So when you're looking at the relationships involved here, a lot of times you're going to be looking at, is it a direct relationship or an indirect relationship? And so, for example, one of the things we talked about was at AFL, you had to see that the pressure increased, so our number of moles increased. And so understanding those types of relationships are important. So that's one of our examples, is that pressure and my number of moles are a direct relationship. So the idea behind that being that if one goes up, the other one goes up. If one goes down, the other one goes down. And then they'll always do so proportionally. So if this one's doubled, this one's doubled. This one's cut in half, that one's cut in half. So they're always going to be proportional relationships. Anytime you've got pressure and number of moles, that'll be true. But that's also true for anything else we have a direct relationship with. So if we have our Pivnert equation, you have that equation, you can always use that to reference. So if we were to rearrange this a little bit, remember we can turn this. Any luck? I'm sorry. I'm going to move this way. Okay, so I can turn this into this. Everybody in agreement? So far, so good. See how I did that? Okay. So now if I look at this, remember my R is just my constant value. So the reason I do that is because this helps me to remember what the relationships are, whether it's direct or indirect, between my compounds. When you've got values on top of each other, like pressure and number of moles, they have a direct relationship. So in order for this to be true, if these are constant, when pressure goes up, number of moles also has to go up to keep this value the same. So anything that is divided by each other is going to be a direct relationship. So that means pressure and temperature also have a direct relationship, and volume and temperature have a direct relationship. But the other relationship you're going to see the most is that volume and pressure would have an inverse or an opposite relationship because they are being multiplied by each other. So if pressure goes up, in order to keep that true, volume is going to have to go down. Once again, these are all going to be proportional relationships. Proportional. So if this gets doubled, volume will be cut in half because they have to go opposite ways. Does that make sense? And this, a lot of times if you put in like some real situations, so think about your balloon. If you've got a balloon, you can squeeze that balloon down. That's going to increase your pressure. So my pressure went up and my volume went down. That made my balloon smaller. So, and it has to be proportional to keep track of that. So my R value is always going to end up being the same number. Is there questions on that? Trying to think about the question on the AFL, like I said, related to pressure and number of moles. I'm not going to ask you that same question again, but we could look at any of these other relationships. Anything about that you guys are curious about? Does that make sense? Yes, sir.
So pressure can be measured in with different units?
Correct.
So how does that affect the unit you use for anything else? Doesn't it affect our
Yeah, so it'll change your R value, and the two that we used were your 0.08206 number. So when you use that, the pressure needs to be an ATM. And then the other one was the 62.36, where you're going to be in millimeters of mercury. So you would just change your R value, and then you can leave your pressure in whatever your unit is. So those are both on your equation sheet, and you get those on both tests. So it's in there, it says what the units are. I would encourage you to look at that because that reminds you what the other units need to be. Based on these, your volume has to be liters, your temperature has to be Kelvin, number of moles obviously has to be moles, and then your pressure you would just match to whichever R unit you're using. You know, think about it like you might have to read the question. If it's a multiple choice question, you might have to check your answer to see if you are solving for pressure, what the unit is, that kind of thing. Yeah, you made me think of something else I was going to say, but now I forgot it. Yes, ma'am.
How can we apply this to like figure out partial pressures?
I think that the only places I could think of this relating to partial pressure would be that understanding that if you have multiple numbers of moles, then the sum of all of those moles has to also be the sum of all of their pressures. So you could, I think the questions we've seen with that would be like your Pivnert equation.
Mm-hmm.
And so if you had multiple different number of moles, you could add them all together and then plug them in for your number of moles, and that would solve for your total pressure.
Okay.
And that would be the instance where you would see that for the most part. Other questions about that? Did you guys have one back there? Questions? Okay. So what would be the relationship between volume and number of moles? I noticed I didn't put that one on here. Would that be a direct or an inverse?
Direct.
Yeah. Okay. So I think then that sort of addresses the fact that all of this is going to be based on gases behaving the way we want them to behave. And so we call those concepts all our ideal gas laws. And we based this foundation of knowledge on our kinetic molecular theory. So let's talk about the kinetic molecular theory for a second. Is that okay? So in our kinetic molecular theory, there are 5 points to the kinetic molecular theory, but only 4 of them we focused on for this unit. One's going to come up when we come back from break. Just saying that, so we talk about it more later. So you've got the main idea that temperature is directly proportional to the kinetic energy. I don't like abbreviating, but I only have so much room on my board. So you'll usually see me say kinetic energy is KE. Try to remind you not to abbreviate. Gases are in constant random motion. Those are going to be very true. We know those are the ones that tend to hold true in all situations. There's some things we'll talk about a little bit more with those. But the next 2 are a little less true. So we assume they have no volume. And we assume they have no attractive or repulsive forces. Attract, repel, that's what I wrote. Because once again, abbreviating. So these are the points of the kinetic molecular theory that are going to be relevant to this unit. So if a gas behaves the way it's supposed to, these 4 things are going to be true. One of the things, and then that's sort of how we then figured out how pressure and volume and temperature and number of moles all relate together. So if those are your 4 main ideas, one of the things we're going to talk about a lot is how we can either get a gas to behave like it's supposed to, follow the ideal rules, or not. What situations are going to make them less likely to be appropriate, I suppose. So when we were looking at things being ideal, we're going to be mostly looking at these 2 things. And since this is our unit on intermolecular forces, The fact that we assume that they have no attractive or repulsive forces are the ones that come up the most often in deviations. So not being like an ideal gas law, because that's what this unit's about. So if we assume that gases don't attract each other, then the stronger the intermolecular force, the further it's going to deviate. So if we have a strong IMF, that means you have a high deviation. There's various things we could do to get it to deviate. One of the things you're going to look at is how temperature and pressure impact those deviations. So when I have low temperatures, we do not have the energy that is needed to overcome those intermolecular forces. And so low temperatures cause your molecules to have stronger intermolecular forces and thus more deviations. So low temperature means not enough energy to overcome. I had lost a C in there. And so stronger IMFs, which then leads to more deviation. Higher pressure leads to your molecules being closer together. And if we have more molecules closer together, they're going to run into each other more often, leading to more opportunities to attract each other, leading to stronger intermolecular forces. So higher pressure equals more collisions, which equals stronger IMFs, which equals more deviation. And being comfortable with those situations and the points of the kinetic molecular theory are definitely something you're going to have to be able to do on the test. So I could also flip this around. This is going to make it like these are the most real, aka largest deviations. So then the opposite would be true at high temperatures. Then we've got plenty of energy to overcome. So that's weaker intermolecular forces. Lower pressures, you have fewer collisions, so weaker intermolecular forces. Those would make the gas more ideal. So be able to go both ways. Yes?
When it shows you the chart with the line that represents like the gas constant, and then it has like all the different gases on it, how do you tell which one's deviating?
So I think it depends on what the chart looks like. I think that that's the one you had on your FRQ. You weren't graded on which gas you picked because at different pressures, they deviated differently. So you were looking for, can you explain how the kinetic molecular theory leads to deviations? If you were expected to be able to pick one specifically, then you'd have to have a chart that was much clearer. Does that make sense? Okay. I think the one we did in the notes was a little bit more just like straightforward. The one on the FRQ was a little more crazy. There's only something out there. I was going to say something else. Oh, I was going to talk about temperature. So before I do that, questions about this? Yes.
So if they have a high temperature, they would still deviate a little bit because they still have intermolecular forces, just less.
Yeah, and so then then the next factor to come into play would be polarity. And I want to talk about polarity and the mass will both be involved here in a second.
When you say not enough energy to overcome, is that overcoming the forces?
Yeah, the intermolecular forces between those. Right. Okay. So if we're looking for strong intermolecular forces, then other things that are going to play a role would be things like the polarity. So things that are polar, remember, are going to have stronger intermolecular forces just naturally because they have that fuller charge. Fuller? They have they're a charge compared to something that's not charged. Partial charge, that's the word I was trying to say. And so if it has a partial charge, it's going to naturally have attractions because that's a stronger Coulombic attractions. When you have two oppositely charged items, they're going to be attracted together. So a polar compound you would see is going to deviate more than a non-polar compound for the most part. So non-polar tends to be more ideal because they have the weaker IMFs. However, what could we do to a non-polar molecule? What is an instance when non-polar molecules might deviate more than a regular non-polar molecule? The bigger they get. So larger molecules are more polarizable. So that could potentially allow them to deviate more because their electron cloud is larger, further from the nucleus, more easily distorted. I'm going to say distortable. I don't know if that's a word. Oh, there's a bad glare. This word says larger. Can't read that on the thing. And that word says polarizable. Okay. Questions there? Okay, and last but certainly not least, remember when we talked about the temperature? So it is true, things that have equal temperature are going to have the same amount of kinetic energy. AP likes you to know that. They talk about it a lot. So it's important that you recognize things that have the same amount of energy have the same temperature, have the same amount of kinetic energy. That's a big topic. Really important. That'll be something we talk about. I think we've talked about just about every unit so far. Most of the units in the spring, we're going to keep talking about it, okay? That's true. One way that affects this unit is the fact that because molecules have the same kinetic energy but different masses, that you might actually have all the same parameters and one's able to travel faster than the other. So if you have a larger mass but the same kinetic energy, that'll cause it to move slower. So think about throwing a bowling ball. We use that as an example. The bowling ball versus a ping pong ball. I almost said a penguin. Don't throw penguins, that's me. So if you go to throw a bowling ball and you throw a ping pong ball, remember you're going to throw them with roughly the same amount of energy because you're just only so strong. Okay? And so because they have different masses, the ping pong ball is going to go much further than the bowling ball. It's also going to go a lot faster. So when you're looking at your kinetic energies, it is important to recognize that they have the same kinetic energy, but the speed that they're going to go will be affected. That's less important in general than understanding this proportional relationship. However, in this unit, it becomes kind of a big deal. Bowling ball, penguin. I should quit. All right, bowling ball, ping pong. That's what that says, not penguin. Okay. So do you guys have any questions for me about that? Okay, I think that kind of covers kinetic molecular theory for off the top of my head. Are there questions we've kind of dealt with that you feel like, is this that topic, and maybe we can talk about it?
Can you talk about STP?
Mm-hmm. Yeah. So STP stands for your standard temperature and pressure. So standard temperature and pressure so you have some particular relationships there. And so each of your values has a specific, each of your quantities, pressure, temperature, volume, has a specific value at STP. So when you're at STP, the one we deal with the most is going to be the fact that we have 1 mole is equal to 22.4 liters. Your temperature, we would usually say is 0 Kelvin. And 0 degrees Celsius, 273 Kelvin, sorry, and 1 ATM. So you'll typically just see it written as S at STP. And so then when you use this relationship, then the nice thing here is that your number of moles, remember we said it doesn't matter what your substance is. So oxygen, hydrogen, whatever it is, they're all going to behave the same way. And they're going to fill exactly a volume of 22.4 liters. So then you can use this in stoichiometry. The nice thing here is it allows you to circumvent the ideal gas law. So you don't have to plug your values into PV equals nRT. You can just do a quick conversion and it'll save you some time. But you could also plug these values into PivNert and solve an equation that way. It'll get you the same answer. That's pretty much the way that.
Do you have any problems with practice using STP?
So the things that we used that the most with, it's not as big of a topic as some of the other things we have. I feel like the places that we used it would be like finding density of a substance. So if I said, trying to think. So if we were at STP and you had, I can't think of any problems. Like a compound, let's say oxygen gas. You needed to know its density, right? I think that's the kind of problem we've done. So you know oxygen gas has got to be O2 because it's diatomic. So that's a concept you have to remember. So if you go to add it up, then we know that if you had 1 mole of it, it would be 32 grams in that mole because oxygen 16 if you looked at the periodic table, right? And so then if you wanted to establish its density, density is always grams per liter. Sometimes it's grams per milliliter, so read what the question says and make sure you know. But probably in this instance, it would be grams per liter. So then if you go to figure it out, I've already got my grams, but I need to change it from grams to per mole to grams per liter. So you can use that conversion we just talked about and the fact that at STP, my number of moles is equal to my number of liters. So if I said in 1 mole, which I'm going to put on top so that my moles can cancel out, I have 22.4 liters, which I'm going to put on the bottom because I want grams over liters. Then I can solve, and when I divide this out, that'll tell me what my density is at STP. I think that's the most common way we used this problem this unit. Questions on that? Amira, does that cover all your STP type questions? Okay. So then, anything else gas laws related that you guys are curious about? Any other problems we've gone through you mean to rework? For sure, you need to know how to solve PivNert with or without a calculator. Understand how to go from, if you've got grams of one compound, switch it to moles of another, plug it into the PivNert or vice versa. Do you feel comfortable being able to do that, or would you like me to create a problem like that? How many people like to see a problem like that? Okay. Then we're going to move on to trends within the London dispersion. I might kind of cover both of these, and that'll go with our boiling point. And so the biggest properties, if I can remember off the top of our head, we talked about were boiling point, vapor pressure for sure. You want to be comfortable with both of those. Volatility, surface tension, hoping I'm not forgetting any of those. On our learning target sheet, I have a place where I did parentheses of all the properties. Are there any properties on there that, I know viscosity is probably there, but I told you that's not on the test.
Solubility.
Solubility.
Yeah.
That's a good one. Hardness will come more with alloys.
Okay. Yeah, I think that's it.
Okay, thanks. I just want to make sure I wasn't missing anything. Thought solubility is a good one to talk about. Okay, so when we're looking at these properties are all going to be dependent on how strong your intermolecular forces are, or your regular intramolecular forces, your atomic bonds. Since this unit is about IMFs and not the atomic bonds. That's where I'm going to focus here particularly. But if you're studying for the final, then both of them are fair game, just for the future. Okay, so remember that our boiling point is talking about how much temperature it's going to take to break apart those intermolecular forces. So if we have the stronger the IMFs, this is going to equal a higher boiling point. I'm talking about this a little bit backwards, I feel like, the way that these are worded on here. Oh, we'll just get to them. Question? Okay. So higher boiling point means it takes more energy before you can get those intermolecular forces to separate. So you have to keep adding energy to get them to separate. And then once they've finally separated enough, your substance will start to boil. So the stronger the intermolecular forces, the more energy it takes, the harder it is to separate, higher the boiling point. Remember, vapor pressure deals with the idea of how many gases are up here. So this is going to be my vapor pressure. Oh. So if you have stronger IMFs, then you're going to have a lower vapor pressure, because stronger intermolecular forces means it's harder to boil. It is harder to separate your molecules from each other, so they're going to stay down here longer. And if they stay down here, they don't make very much vapor pressure. So the stronger the intermolecular forces, the lower the vapor pressure. You're going to shout at me if you have a real question, right? I don't know, it seems to have stopped recording me. Oh, it didn't. Hi, people. Okay. Okay, so, sorry, I got distracted. Questions on those two yet? Okay, volatility goes right along with the idea of vapor pressure, really similar concepts. Volatility is the likelihood of it to be able to evaporate. Kind of thinking about somebody that's really volatile, doesn't take a lot of work to make them mad. They'll explode on you with no work. So same thing happens if you have molecules. So the stronger the IMF, the lower the volatility, because the less likely it is to evaporate. So they're going to hold together really well. Weak intermolecular forces break apart really easily. So weak intermolecular forces would have high volatility. Okay, so surface tension deals with once again, how likely those molecules at the surface are holding together. So more surface tension is going to be equal to stronger intermolecular forces. Those guys are holding each other together, so they make a strong surface. So strong intermolecular forces leads to high surface tension. So those little bugs that can crawl across the top of the water, they can do that because water has hydrogen bonds, which are fairly strong. So that surface is pretty strong as far as the little bugs are concerned. So they travel across the top. I'm sure those bugs have names. Then solubility is slightly different. So before I talk about solubility, are there questions on any of those properties? Okay. So remember, solubility, substances that have similar intermolecular forces are more likely to interact with each other. So I'm going to switch gears a little bit and erase this and kind of talk about intermolecular forces in general, and I'll establish solubility as we go. So remember, anytime you're comparing two substances, I really encourage you to make that chart where you talk about compound A versus compound B, whatever those happen to be. And then here you would say what bonds they have, whether it's ionic, covalent, metallic, although I don't know why it would be metallic. I put too many T's in that. And then if it's covalent, whether it's polar or nonpolar. And then lastly, you would want to tell me what types of intermolecular forces. So if it's nonpolar, London dispersion is all you have. Whereas if it's polar, you're going to definitely have dipole-dipole and London dispersion. And then what instances make you have hydrogen bonds? Good. So you have to have hydrogen and the phonophores, either fluorine or oxygen or nitrogen lead you to hydrogen bonds. So this may or may not be in the list. Okay. So remember, typically speaking, these are partially charged and these have no charge. So that typically leads to these having greater Coulombic attractions than here. So in general, these have higher Coulombic attractions. In general, these have lower Coulombic attractions. And that's due to having no or a weak charge. And this one having a partial charge. So typically, we have that phrase, like dissolves like. Don't put that in an FRQ ever. Just good for you to remember that as far as solubility goes, substance with similar intermolecular forces are going to interact. Now, it's not true that if they have different intermolecular forces that they can't interact. It just means they're less likely to interact. So when you draw this chart, one of the nice things about AP is I think they're pretty clear about what they want you to talk about in an FRQ. So on a point, if it says some information you don't understand, and then it follows with explain this based on intermolecular forces, then if you have no idea what they're talking about, take your two substances, build yourself a chart, and look for similarities. Say, well, they have different intermolecular forces, so they're not as likely to interact. And just try to go with something if you're totally lost. But it'll say in there, explain it based on intermolecular forces. So a good tip would be to figure out what those are. Good question.
If something isn't proven, but it's like we're talking about, would you say it's unpolar?
You wouldn't. You would just leave this blank. I just draw a line there, and you would draw a line here. So like on this test, the situation where you're most likely to see that would be if you had over here, this would be ions. And so then now you have something that has a full charge versus something that has a partial charge.
Which is stronger.
Right, which leads me to my strengths of attractions. And I might want to talk about that, and then I'll come back to energy at the end, if that's okay. So, yes, sir.
So I understand why like polar substances will interact because they have like those charges, but why do non-polar substances interact?
That is because of the concept of an induced or instantaneous dipole. Were you here when we talked about that in class?
Yeah. But
Okay.
So like, why wouldn't
Let's-
polar induce a dipole and a non?
Well, it would, and that's why a polar compound could actually bond with a nonpolar compound, but it's much more likely to react with something that is already polar. It doesn't have to get the charges, electrons to move. That's why it's more likely. I don't foresee a situation where you would have to explain how a London dispersion force works, but understanding that it does work is important. Okay, so in general, when we're looking at comparing the strengths of your bonds, remember that an ion dipole is going to be the strongest as far as intermolecular forces go that you're likely to see. Should I go back even further and talk about covalent ionic metallic? Okay. So then we wouldn't have an ion hydrogen bond because the hydrogen bond implies that you're looking at two molecules that have the hydrogen phone connection. And so if it's an ion, it can't have that. And so then as you keep going, if you look, you're going to have hydrogen bonding. I'm looking at strengths here. So that's going to be strongest. Hydrogen bonding would be strong. Then we've got dipole, and then some combination of those being like dipole, London dispersion, and then just London dispersion forces in general is the typical kind of flow of strength. Those get strong. Now we know there's places that we can adjust that because like if your London dispersion forces you're told are stronger for whatever reason, like that vapor pressure problem we were doing the other day in class, then you have to assume, well, the only way these get stronger is because they're larger, so they might be more polarizable. So that's like the most common way we would like break the rules here. Cool.
Can you explain at the top why dipoles with ions?
Why dipoles what?
Like with ions?
Oh, if you had a relationship between an ion and a dipole. So let's say you had salt water. That's an example we used a bunch in class. So you'd have like your Na plus and then your water molecules all around it with your oxygen. And so remember, so it's important to understand that because this is fully charged and this is partially charged, pretty strong still. So you would have the ability to have the a really strong attraction here because you have a full charge and a partial charge. That's a lot of Coulombic attractions happening here. Hydrogen bonding, that's going to be the most charged you can get in a polar compound. So that's why it's the next in strength. So like this is just kind of a general rule of thumb. Questions for me on that? So then energy comes into play because we're going to be talking about strength. Well, if we're talking about strength, then breaking or making those bonds is going to be talking about energy exchange that's involved in that. And so we talked about solubility. I think we've covered any questions about that before I erase these. Last thing we'll talk about is energy. So the biggest place that energy is going to be involved in this unit is the concept of breaking those bonds and making those bonds. And so remember that when we're breaking bonds, in this instance, we'll be talking about breaking intermolecular forces. What you're doing when you're breaking an intermolecular force, you're taking something that was bonded and you're asking them to be separate. Compounds bond in order to move to a low energy configuration. So when they're bonded equals low energy configuration. So breaking that bond, you have to move it to a high energy configuration. So you're going to have to add energy. So breaking intermolecular forces, you have to add energy. So you can move it from the bonded phase at the low configuration to the high configuration. If something's unbonded, it's at a higher energy. Remember, these are all like typical, this is like general rules of thumb. So that means if you're going to be making an intermolecular force, you're going to be moving it from an unbonded phase that's high energy to a bonded phase that's low energy. It doesn't need the extra energy that it was using to be in that higher state. So you're going to see a release of energy. So this unit, we talked a lot about phase changes. Remember, when you're doing phase changes, you move from a solid, a liquid to a gas, you're going to be breaking intermolecular forces. So it takes adding energy. And then the strength of the bond will be dependent on how much energy it takes. If you're trying to boil salt water, you've got that ion in there. So that's going to be a really strong bond. It's going to take more energy than if you were trying to boil regular water, because that's going to be just hydrogen bonding. Even less energy to boil acetone. Don't boil that because it's really volatile. It'll catch on fire. Kind of see the connections there. So, I don't know. What else do you guys have questions about? That's mostly where energy was applied.
I was kind of confused about like polarity and like the chromatography lab, like how they're connected.
Okay, before I switch gears to that, questions here? That's a good question though. I'm going to get rid of energy here. All right, chromatography lab, a good place to go because that was our only lab this unit. So for sure going to be asked about that on the test. The chromatography lab you had your little setup, and one of the big things to understand, you've got the 3 different phases, right? So you've got your stationary phase, which is your paper. If it happened to be gas chromatography, you would have a gas. There's column chromatography, there's a liquid. So there's like different places you could use your substances, but the idea that you have a stationary phase, our example used in class was the paper one. Then you have your mobile phase, which is always going to be your solvent. So for our purposes, we put our solvent in the space down here, drew a line, and added our dyes, our solutes. Okay. So then as the solvent traveled up the paper, it was able to grab onto these different dyes and carry them different distances. So we'll call this dye A and dye B. And they went different distances, okay? So the mobile phase, it's important that it's able to travel the distance of the paper. So it has to have somewhat strong intermolecular forces to be able to travel the distance of the paper. We know that because in class we saw that the alcohol didn't travel as far as the water. And so the water was able to go further, and we know it had stronger forces. So we know as far as paper is concerned, that was an important correlation. Whereas the solutes are being attracted to both the stationary phase and the mobile phase. So what we're looking for is the ability for them to travel, but also be able to be separated. So that's where your polarity kind of comes into play. Since we know that water is more polar, we're looking for their substances that are able to travel. The more polar it is, the more likely it is to be able to travel up your paper. If we're looking for a solute, its attractive forces are going to be attracted to both the paper and the solvent. So the stronger the intermolecular forces of the solute, the less far it's going to go. So if the solute has strong IMS, it's going to be left behind. And so this one we would say is going to have the stronger because it has this attractive force for the paper and the water. So it's holding onto the paper, and as the water goes by, it pulls it some of the way, but the strength leaves it behind. Whereas this one has fairly weak intermolecular forces. So as the water sweeps it by, it carries it up the paper further, and eventually they'll be left behind. Anything else you guys would want to know about that? Does that answer whatever you're asking me? Perfect. Have a lovely day. I'm here after school if you guys have questions.